Hello everyone, welcome to this another instructional video. Today's presentation is related to this unit, Geometric Optics. And the title of this presentation is Images Formed by a Convex Lens. In this presentation class, I will discuss about how images are formed in a convex lens and to elaborate further the concept of the law of refraction of light. Now, in line with this presentation, I have here the lesson outline for this topic. Now, we will start with the concept of image formation. Here, we will talk about the characteristics of the images formed by a convex lens. Now, then we will going to proceed in the second section, the concept of the construction rules. So these rules are very important for us to understand because this is a way for us to determine the images formed by a convex lens. Then we are going to apply these rules to section number 3, the graphical construction of image formation. Here, we are going to learn the steps on how we determine the image formed by a convex lens using a graphical method. After we discuss the concept of graphical construction of image formation, then we will proceed to section 4, which we are going to discuss about the nature or the characteristics of the images formed by a convex lens given the position of our object at a given distance, and also we are going to look into the result of these images as they are being projected in our translucent screen. And then the fifth one, we will discuss about the concept of magnification. So we will define what is magnification, and also we are going to derive the equation for magnification. And the last section is all about the lens formula or lens equation. Here, we will talk about the derivation of the lens formula and apply these formula to problems related to the convex lens as to how the image are formed. Okay, before we proceed to section number 1, let us have this warm-up discussion first. Okay, lens on a watch. Have you seen this kind of watch before? Yes, probably you have a watch like this, or your parents has a watch like this. Now, what is interesting in this watch is that there is a lens over the date display so that the date can be seen more easily. The question is, what kind of lens is this? Probably you have already a good guess. Basically, this is a convex lens. Now, convex lens class has been used to any or to many applications in our day-to-day endeavor. One application is this one being used in a watch. Another application is the lens is being used for cameras. Cameras for your phone, or the cameras that are used by the professional photographers. So basically, lens is or has been widely used in many applications. And that is why it is very important for us to learn and understand the properties and the physics behind this material or this device. To start with our discussion on images formed by a convex lens, let us have first this experimental setup entitled Seeing an Image Formed by a Convex Lens. Here, we are going to look into the different characteristics or nature of the image formed by a convex lens. Now, you can do this in the laboratory by following these procedures presented in this presentation. First thing that you are going to do is, of course, you gather the materials for this experimental setup. Well, you have here this what we call translucent screen. You have here a convex lens, and of course, you need to have a source of ray, which is known as the illuminated ray box. Now, the first thing that you are going to do is that you place a convex lens 50 centimeter in front of a letter F illuminated by a ray box. You move a translucent screen on the other side of the lens to capture a sharp image. You remove the screen and see if the image can still be observed. Now, second step is that you put the lens 5 centimeter away from the letter F and see if the image can still be observed. Now, to understand exactly this experimental setup in action, I want you to watch this video clip, which is all about seeing images formed by a convex lens.
Place a convex lens in front of an illuminated letter F. Place a translucent screen behind the lens. Adjust the position of the screen until a clear image is obtained. Since the image can be captured on a screen, it is a real image. If we move the screen slightly closer to or further away from the lens, what will happen to the image? Now, slowly remove the screen. Can you still see the image? Move the convex lens towards the ray box until their distance becomes 5 centimeters. Can you capture the image on a screen now?
Section 1, Image Formation within a convex lens. Now, in that video clip that I presented to you, we can draw two important properties of the images formed by a convex lens. Now, according to the presentation, convex lens can form real and virtual images. Now, the question is, what is a real image and what is a virtual image? Let us discuss these two characteristics of images formed by a convex lens in this presentation. Okay, real images. Consider a small object that is viewed through a convex lens. Now, our object is located right here in this particular point, and we have here a convex lens. And this is you, where you are the observer. Now, consider this point Y here. So what is this point Y? Well, basically, this point Y is the point where these light rays, or shall we say the refracted rays, are converging at that particular point. Now, light rays from the object converge to point Y, as I've mentioned. If we look at the lens inside the region bound by the dotted lines, example at point P, so for example, this is you here, this is the observer, and this is the boundary, the dotted line boundary, a cone of rays will enter our eyes. So this is the cone of rays that will enter our eyes. Now, since the rays cross at Y, our brain perceives the object at this position. Therefore, we be able to see an image at point Y. Therefore, in this case, we call this image that is located at point Y as the real image, because as light rays really diverge from it. Now, we cannot see image at Q as no light from the object enters in our eye. So our Q is right here. So you are here. This is the observer. And since the cone is away from our point Q, therefore, you cannot see exactly the image because, as I've said, there is no light from the object that enters our eyes. Now, we can place a translucent screen at point Y to capture that image for viewing from different directions. Now, remember this. Only real images or real images can be captured by a screen. If the screen is moved forward or move backward, so in this case, we can move this screen here or we can move the screen on the other side. Therefore, in this case, a point on the object becomes a small patch of light on the screen, and as a result, the image will become blurry. Okay, so that is real images class. Now let us talk about what virtual image is. So let us consider an object that is viewed through a convex lens placed very close to it. So you have this object and it is placed very close to our convex lens, and this is you, the observer, at point P. So light rays from the object still diverge after passing through the lens. So in this case, again, there is still a refraction of light within this convex lens. Now, our brain then will perceive them by extending them backward. So in a way, in order for us to see exactly the image, our brain will going to perceive that this image is located right at the other side, or by extending them backwards. Now here, we call this now our point Y. Extended rays meet at point Y, therefore our brain perceived the image there. As a result, we call this as our virtual image, because as no light rays actually pass through Y. Now, virtual images class cannot be captured on a screen. Okay, in short, class, there are two images that are formed in a convex lens. The first one is real image, and this real image is located here in this side. Okay, this is where your real image is. And the second one is a virtual image, where the virtual image is located somewhere in this side. So in this particular side. So in short, when the image is located together with the object position, so this is where your object is, there that image is known as virtual image. While when the image is located opposite or the other side of the position of the objects, where it is located here, is real. Okay class, we are now in section 2, construction rules. In this section, we are going to investigate how light rays are refracted when they pass through a convex lens. In order for us to investigate that, let us have this experimental setup entitled Construction Rules for a Convex Lens to see exactly how does light refracts in a convex lens. Now this experimental setup, you can do this setup within the laboratory. All you have to do is to secure a convex lens and also a ray box where you can illuminate your source of light. Now this is how we do it. First, you direct a light ray at a convex lens along the direction as shown. So the first is that the light ray is parallel with respect to the principal axis. And second, it is directed to the focus prime. And then the third one, it is directed to the optical center. Then you observe how the ray passes through the lens. Now, to see this one in action, I want you to watch this video clip in relation to this experimental setup, the construction rules for a convex lens.
Direct a light ray from a ray box. Slowly slide a convex lens perpendicularly across the light ray. Notice how the ray passes through the lens at different positions. When the light ray passes through the optical center of the lens, the ray travels straight without bending. Where is the optical center of the lens? Draw a straight line that passes through the optical center and perpendicular to the lens. This line represents the principal axis. Direct several light rays parallel to the principal axis onto the lens. Notice how the rays are refracted. The point where the light rays converge is the focus of the lens. Measure the focal length of the lens with a ruler. What is the focal length? Finally, direct a light ray to the lens along 3 different directions as shown. How does the light ray pass through the lens in each case?
From the experimental setup, we can summarize the construction rules for a convex lens. Rule number 1. For a ray parallel to the principal axis, it is bent so that it passes through the principal focus on the other side of the lens, as shown with this drawing. Rule number 2. A ray passing through the principal focus F prime, like this, emerges parallel to the principal axis, as you can see like that. And rule number 3, a ray passing through the optical center travels straight on, as shown in this diagram right here. So once again, there are 3 important construction rules that you need to remember. Rule number 1 is shown through this diagram right here, and rule number 2 is shown through this diagram right here, and rule number 3 is given by this one. We are now in section 3. This is graphical construction of image formation. Now here we are going to learn about how to determine the image formed by a convex lens using graphical method. So in order for us to do that, we have to employ these important notations or symbols so that we can perform the construction in an efficient manner. So ray diagram, by the way, are useful for locating images formed by lenses and figuring out their nature. We can use this symbol to represent convex lenses and apply the 3 construction rules. So this symbol class is exactly the symbol that we use for a convex lens. Later in our discussion, we will learn the symbol about concave lens. Now again, we use this for the determination of the image formed by a convex lens in a graphical way. Now, these are the steps for drawing a ray diagram for a convex lens so that we can locate exactly where our image has been formed. Okay, now step 1, you draw the principal axis and the convex lens. So this is your convex lens and this is your principal axis. By the way, your principal axis would or should always be perpendicular with your lens. Step number 2, you're going to mark your F prime and 2F prime on the principal axis on one side and F and 2F on the other side. So this is the 2F and the F, while this is 2F prime and F prime. So our prime values will be in the left side of our coordinate plane in a sense. We call this coordinate plane, and our f and 2f will be on the right side. Okay, make sure that 2f prime is equal to 2f, which is 2 times the focal length. The distance here should be equal. Now, let's move on to step number 3. So you need to draw the object as an arrow upright on the principal axis at the given position. So from here, you are going to draw your object. So for example, if your object is located somewhere beyond 2f prime, so you can see here, now your object should be drawn as upright and bold arrow. Okay, now step number 4, we draw rays with arrows to indicate directions from the tip using any 2 construction rules. In this step, you're going now to use the construction rules that you learned in section 2. So here we have this one. Our ray is parallel to the principal axis. Now it will refract towards the focus, and we have also a ray that is passing through the optical center. Here it will not refract, and in this case you have an intersecting point somewhere there. This is the intersection here. If the refracted rays cross the intersecting point, is the location of the real image of the tip. So meaning this tip right here is exactly located somewhere here. Otherwise, use dotted lines for extending rays backwards to locate the virtual image. So here we locate exactly where our image is. So the real image as a vertical arrow, and similarly draw a dotted arrows as a virtual image. So if this is a virtual image class, you're going to draw this in a dotted arrow. So to have a good understanding of this graphical construction of image formation steps, let us have this example. So an object is placed between f prime and 2f prime from a convex lens. For rays, you have P, Q, R, and S. So you have P, Q, R, and S. Now, from the object are incident on the lens. Question: complete the rays and locate the image. Okay, so to complete the rays, we need to apply the construction rules. So the construction rules is very straightforward. You have this parallel one, and you have this, the Q is parallel to our principal axis. You have this R, which is directed to the optical center. You have this ray S and ray P. There you go. You can see exactly how these light rays are refracted in the lens. So you can have this image as shown in this diagram. The question, letter B, is it a virtual or a real image? So the answer should be a real one. It's a real image because it is located here on the opposite side of our object. Now, virtual is if it is located in this side class. Another information that you need to take note: parallel rays not parallel to the principal axis always converge to a point on the plane. This plane passes through the focus and perpendicular to the principal axis. So this is we call this one focal plane. If a screen is placed on that focal plane, it can capture the image of a distant object. Okay, that's the end of section 3, graphical construction of image formation. Section number 4. The title of this section class is Position and Nature of Images. Now in this section, we are going to discuss about the characteristics of the images formed by a convex lens, given that our position of our object varies from point to point. We will also look into the position of our images formed by the convex lens once we adjust the position of our object. Now, to understand this concept, let us have first this experimental setup. The title of this is Studying Images Formed by a Convex Lens. Now, this is how we do this in the laboratory. Let us set up the apparatus as shown in this diagram right here. Now, we have a convex lens that is put in a holder, and you have a lamp housing where this is where your ray coming from, and you have a translucent screen where you are going to capture your image. Now, you are going to measure your object distance, and we denote that one with the small letter U. Other textbooks, they use this symbol D sub O as a symbol for your object distance. Also, we are going to measure the image distance, that is the distance from your translucent screen going to the convex lens, and that is denoted with the small letter V. Now you start with a large object distance, given that your U, this is your object distance, is greater than twice of the focal length, or 2f. Now move the screen until a sharp image of it is formed. Now you repeat step 2 with the smaller object distances and observe how the image changes. Now, in order for us to see this one in action and fully understand what I'm talking here, I want you to watch this video studying images formed by a convex lens.
Set up the apparatus as shown. Place the convex lens at a large distance from the ray box. Adjust the position of the screen until a sharp image is formed on it. What is the nature of the image formed? Repeat the above steps with smaller object distances. How do the image and the image distance v change as the object distance u decreases? Further decrease the object distance until no image can be captured on the screen. If the screen is removed, can you still see the image of the letter?
From that video presentation, we can infer important characteristics of the images formed by the convex lens. We describe the nature of an image by pointing out whether it is inverted or erect, magnified or diminished, real or virtual. So these keywords, class, are very important in our discussion about the images formed by our convex lens. You have to take note of these keywords because you use this often. Now, experiment 3C, or that experimental setup that I showed you, shows that the position and nature of the images changes with the object distance. Our image formed by the convex lens is dependent to our object distance. Now we can use the construction rules that we have learned in our previous section to find exactly the location of our image and the nature of our image formed by a convex lens. In the next slide, I would like to enumerate to you different image characteristics of the image formed by the convex lens. Number 1, if your object is located at infinity. Using the construction rules, we be able to determine exactly where the image is located. So our image is located somewhere here. So the image position is on a focal plane, while the characteristic or the nature of our image, it is real, it is inverted, and it is diminished. That is when the object is located at infinity. Situation number 2. Our object is positioned beyond 2f prime. What will be the characteristic of the image formed by a convex lens? Our image is located between F and 2F. So from our construction rules, you will find exactly where the image is located. Moreover, the characteristic or the nature of our image is that it is real because it is located here in this side. It is inverted because you can see it is inverted with respect to our object, and it is diminished. It means that it is smaller compared to our object. Situation number 3. Our object is located at 2F prime. Using a ray diagram right here, we'll be able to determine exactly where our image is located as it is formed by our convex lens. Now, the characteristic of our image are the following. Number 1, of course, the position is at 2F. It is real, inverted at the same time. It has the same size with our object. Situation number 4 is that our object is located between F prime and 2F prime. As you can see in this ray diagram. Using our ray diagram, we'll be able to find again our image located at this point right here. The image position class is beyond 2F, and the image nature is real, inverted, and it is magnified, meaning it is bigger compared to our object. Situation number 5 is that our object now is located at F prime. So this is where our object is. Looking at this picture right here, we be able to note that there is no such image being formed. So refracted rays are parallel, therefore the image formed is at infinity. Thus, we will not be able to see image in our lens because no image is formed. Now, situation number 6. In this case, class, the object is located at this point within F prime. Using our ray diagram, we be able to trace exactly where our image is located. So our image is located right here at the back. So our image is located at the same side of the object, and our image in this case, the characteristic is virtual because it is at the same side with the object, and it is erect, as you can see. Same with the orientation of our object, and it is magnified. Now notice here that we are using a dashed line to indicate that this is a virtual image. And also, we use a dashed line here to extend our light rays or refracted light rays. Now, in conclusion, class, for a convex lens, the nature of the image depends on the distance of the object from the lens. We are now in section number 5. This section, we are going to discuss about the concept of magnification. What is magnification? So by definition, class, magnification is simply the ratio between the height of the image and the height of the object. And it is expressed by this formula. M is equal to H sub I divided by H sub O. We can also express magnification in terms of the image distance and the object distance. We can define magnification as the ratio between the image distance over the object distance, and that is denoted by small letter v divided by small letter u. Other textbooks, they use the symbol d sub I over d sub o. Since magnification is a ratio of two numbers, therefore the result will be a number without a unit. In order for us to interpret that value, let us have this concept. When the magnification is greater than 1, or your value of magnification is greater than 1, therefore the image is magnified. It signifies that your image is being enlarged. When the magnification is less than 1, therefore the image is diminished, meaning becomes smaller. When the magnification will be equal to 1, then we interpret it that the image is of the same size with the object. To understand fully this concept magnification, let us have this example. We have an object that is 5 centimeter high and 15 centimeter with respect from a convex lens, and this convex lens has a focal length of 10 centimeter. The question is, determine or find the position and magnification of the image. What we are going to do first is we can draw a ray diagram to illustrate exactly how does the image is formed. Now, from our ray diagram, we be able to see exactly the characteristic of our image. In this case, our image is located somewhere here, and of course, our image is inverted, but it is real. Now, the question says we want to determine what is the position of our image, or simply the image distance. To calculate the image distance, what we have here is equal to 30 centimeters. Now, since we know already the position of the image, then we can calculate the magnification. Now, our magnification is equal to 2. Since our magnification is equal to 2 and 2 is greater than 1, therefore our image is magnified. And that is exactly how we use the concept of magnification. We are now in the last section of this presentation, images formed by a convex lens. And this section is all about the lens formula. In this presentation, I will going to discuss to you how does the lens formula being derived. In order for us to understand the derivation of these formula, let us look into this experimental setup. So inside the laboratory, you can perform this experimental setup in order for you to be able to derive the equation of the lens formula. Now, to do that, you have to set up the apparatus using a convex lens with a known focal length, and you set the object distance u greater than the focal length. Second thing that you're going to do is you move the screen until a sharp image is formed, and you record your object distance and your image distance. You repeat this step with different values of your u or your object distance, and you record the corresponding value of your image distance. To fully picture out how this experiment being done inside the laboratory, I want you to watch this video clip.
Set up the apparatus as shown. The object distance should be larger than the focal length f of the convex lens. Adjust the position of the screen until a sharp image is formed on it. Measure the object distance u and the image distance v obtained. Repeat the steps with different values of u. Calculate the reciprocals of u, v, and f, and record the results in a table. What can you deduce?
From that experimental setup, we have the following data. Your object distance, u, is given by 100 centimeter. And as a result, your image distance will be 25 centimeter. Also, if you have an object distance 80, your image distance will be 27. While if you have an object distance 60, your image distance will be 30. Also, if you have an object distance 40, then you have an image distance 40. Looking at the focal length, we have a constant value. The focal length is equal to 20 centimeter. Now, if you take the reciprocal for our focal length, that is equal to 0.05. Looking at this data right here, if we are going to take the reciprocal of our object distance and also the reciprocal of our image distance, we have the following value. 0.010 for our 100 object distance, that is the reciprocal for that. And for the 25 image distance, that the reciprocal is 0.040. Also here on this other data, we have the following value. Notice, class, that if you are going to sum up these reciprocal of 1 over u and 1 over v, or the reciprocal of the object distance and image distance, you will be able to get the equivalent value of 0.05. 0.017 and 0.033 has an equivalent value of 0.05, and 0.025 plus 0.025 has an equivalent value of 0.05. So what does it mean, or what does this data tells us? Therefore, from this experimental setup, we be able to derive a relationship which is known as the lens formula, that the sum of the reciprocal of our object distance and the reciprocal of the image distance is equal to the reciprocal of our focal length. We call this equation as the lens formula and can be applied to both real and virtual images. The real is positive convention must be used here in order for us to be able to determine exactly where is real and where is virtual. So for example, class, if your focal length is positive and if your object distance will be positive, therefore the image distance will be positive if it is real, and if it is virtual, it should be negative. Okay, let us have this example and use the lens formula to solve example number 2 that we had a while ago. If you have a value of the object distance 15 centimeter and focal length that is 10 centimeter, we want to determine what is the image distance. Using the lens formula, class, we have the value 1 over 5 plus 1 over v is equal to 1 over 10. As a result, we want to determine our v, and that is equal to 30. When we calculate the magnification, that is equal to 2. And from this formula, we still have the same result as being obtained in our previous example. Now, let us have another example here. Detective Holmes is investigating a crime scene and he puts a convex lens 2 centimeters away from a wall. Now, the image is erect according to his investigation, and then the magnification is about 3. The question is, what is the focal length of the lens? Now, from our given, we have u is equal to 2 centimeter and m is equal to 3. And of course, the image is erect. M is equal to v over u. This is exactly the magnification. And if we want to determine the v, which is the image distance, and that is equal to 6 centimeter. Now, according to our given, the image is virtual. In this case, it is erect and magnified. Now, if our image is virtual, class, therefore the image distance should be taken as negative. So from here, if we are going to employ the lens formula, we have 1 over f is equal to 1 over u plus 1 over v. Therefore, substituting these values, take note that our image is virtual, so therefore it is negative value. Thus, our focal length is equal to 3 centimeter. And that's the end of this presentation. Thank you for watching. Hope you learned something from this material.